So we're talking about the neuromuscular junction. Neuromuscular junction is where the neuron talks to the muscle. This is our neuron, this is our muscle. An electrical signal comes down the neuron and causes the release of acetylcholine from the synaptic vesicles here, causes the release of acetylcholine into the synaptic cleft. That's what this space is called. The acetylcholine will bind to acetylcholine receptors. The acetylcholine receptors are on the junctional folds of the sarcolemma. This is the muscle cell. Everything on the lower part of the word is a muscle cell. The muscle cell membrane is the sarcolemma. So the acetylcholine is released into the synaptic cleft, binds the acetylcholine receptors on the junctional folds of the sarcolemma. Those acetylcholine receptors open as channels to sodium. And so as they open, the sodium, which is high on the outside of the cell, will come rushing into the muscle cell. Sodium comes rushing in through the acetylcholine receptors, which are sodium channels. As the sodium comes in, it changes the resting membrane potential of the cell from minus 90 millivolts, which is a polar membrane potential, raises it upwards. This is called depolarization as it becomes more positive. If it hits minus 55 millivolts in the presence of these guys, then these channels open. These are voltage-gated or voltage-regulated channels, and they are also sodium channels. So as this sodium comes in and dissipates, it causes a change in the voltage here. If I reach threshold, it opens this channel, more sodium comes in, dissipates, reaches threshold, opens, dissipates, reaches threshold, opens. And I've got sodium coming in all the way down the entire length of the cell. As that sodium continues to come in and depolarize the cell, this membrane change, this depolarization is recognized by other parts of the cell, including the sarcoplasmic reticulum. The sarcoplasmic reticulum is a storage place for calcium. There is a lot of calcium in here. And when this voltage change happens, the voltage-gated channels in the sarcoplasmic reticulum open and let the calcium out of the SR, out of the sarcoplasmic reticulum, but that's into the muscle cell. So from here into the muscle cell. In the muscle cell, it can go to where the sarcomeres are. The sarcomeres have the thin filaments and thick filaments. The calcium that came out of the sarcoplasmic reticulum can bind to the troponin, which is on the thin filament of the sarcomere. It can bind to the troponin, which binds, causes the conformational change. That will pull tropomyosin off of the binding sites that are on the thin filament. The thick filament wants to bind to the thin filament, can't because tropomyosin is there. So if you remove the tropomyosin, now the thick filament can bind to the thin filament. So the thick filament has to cock its heads back, and it can bind to the thin filament and pull. And it will keep doing that with all of the different heads, and that is contraction, which will take you from a relaxed sarcomere to a contracted sarcomere, which is shorter. And if you have 100 sarcomeres the whole length of the muscle, that's going to significantly shorten the length of your muscle. We are eventually going to talk about relaxation, but not until next week.